Welcome to the third part of the plutonium chemistry lecture for the Actinide Chemistry course. Again, the readings for part 3 are the same as part 1 and 2, the plutonium chemistry chapter and the challenges of plutonium chemistry. This part is going to have a brief discussion on radiation damage and then a discussion on plutonium compounds.
So we left off previously discussing plutonium metal. We were discussing corrosion properties, and we want to continue this discussion in the fact that plutonium's radioactive. Radiation damage can be induced in plutonium metal. And the decay rate of plutonium-239 is sufficient for the production of radiation damage, and this can include the buildup of alpha particles or helium in the material and radiation damage due to the emission of the alpha particle and the recoil of the uranium daughter. In fact, the recoil of this uranium daughter is what is the prime generation of the radiation damage effects. This is due to the recoil energy of, if you remember from the Q, we could calculate the Q value. We can see how much of the energy goes into the alpha decay, and there's some that goes into the uranium daughter. It's on the order of keV, but that's certainly enough energy to knock crystals off their lattice sites, and vacancies are produced, and the net effect from both the helium and this radiation damage is void swelling. So on the microscopic level, the vacancies will diffuse together and cluster, and what's observed is that the metal swells. And here's an example of some radiation damage. We have an alpha particle, has a range of about 10 micron through plutonium metal. The uranium recoil is much, much smaller, 12 nanometers. Frankel pairs are formed through this, where you have, here's an example of Frankel pairs, where you have vacancies and interstitial. So vacancies are just holes where an atom should be, and an interstitial is an atom sitting in a place where it shouldn't be. So these pairs are formed, they coalesce together, and as we see here, there's a smaller amount of energy, shorter range, but many more Frankel pairs, about an order of magnitude more, are produced from the uranium recoil. And one of the properties of this is that you get, over time, swelling, and you have a void swelling curve. The properties of this void swelling curve, as you see here, there's ranges of what can be due to the void swelling, which is this uranium recoil, and then there's a range for the swelling due to the helium. As we see, the helium, while it does contribute, does not seem to contribute as much as the void swelling. And generally speaking, this swelling behavior has three main components as a function of dose, and the dose is described in dPa, which is displacements per atom, so how many times an atom in the lattice gets displaced. There's an incubation period where you have some dose effect and no swelling is evident. A transition period where we have higher dose and the swelling increases. And then a steady state where there's a relationship between dose and swelling. The actual relationship, the actual swelling as a function of dPa, varies with materials and conditions. All right, now that we've discussed plutonium metal, we can begin evaluating plutonium compounds. There was originally a difficulty in producing plutonium compounds, mainly for two reasons. One, it was hard to get a hold of plutonium, and if you got a hold of plutonium, the purity was not certified. So it was often that the purity of the plutonium metal, or the plutonium compounds that you were using as starting material, was difficult to get into pure forms. Now, development of plutonium compound has been aided by microsynthesis and also the amount of material available. If you remember, when in the first lecture of this plutonium series, we talked about purifying plutonium metal. So a lot of effort has gone into producing pure plutonium compounds used for materials. And much effort, particularly early effort, compounds were characterized by X-ray diffraction. So a very simple compound, and one that we've already talked about, is the hydride. Plutonium hydride can be formed by the reaction plutonium with hydrogen. We get PuHX, where X varies from 1.9 to 3. The hydrogen partial pressure can be controlled to develop the exact stoichiometry of the final product. And variations, and there's some variations in the synthesis, and some of these difficulties in producing the material or characterizing or having or understanding the exact phase diagram are based upon the fact that the hydrogen can deabsorb from the plutonium hydride. The plutonium hydride is a fluoride structure, and if we have something like PuH2, this would imply that plutonium is divalent. However, measurements show that the plutonium is trivalent and the PuH2 is metallic. So what we seem to have is plutonium-3, 2 negative hydrogens, and 1 electron in a conducting band. And this is consistent with conductivity measurements that were performed on plutonium hydrides. Some of the properties of the plutonium hydrides are exploited in some processing. And here's an example of the Aries process, which is shown here, where a plutonium metal will be treated with hydrogen. The plutonium hydride is formed. The plutonium hydride flakes away from the metal, so the plutonium hydride can form into this crucible. It's the plutonium hydride that's in this crucible is heated to 400 degrees under vacuum. The hydrogen is released, and the metal is reformed. So this is a way of taking a shape that may have classification issues and converting it into a metal with a shape that is not classified, and can also have criticality, safety controls associated with it. Other plutonium compounds are the carbides. Carbides have been proposed as nuclear fuel. There's 4 known plutonium carbides listed here. The plutonium monocarbide exists only as a substoichiometric compound, so PuC 0.6 to just a little bit below 1. And these, as I stated earlier, these compounds are considered as candidate for fuels. The synthesis of plutonium carbides, you can use the metal, the hydrides, or the oxides with elemental carbon. So they can be combined together at high temperature, and the carbides are produced. Controlling the stoichiometry can be useful for controlling the final product. Some of the chemical properties: the carbides oxidize in air starting at around 200 degrees. They do react with nitrogen, so this is part of a carbothermic reduction process. So if you wanted to form plutonium nitride, you can take the oxide material, produce the carbide, and then treat that with nitrogen to produce the nitride. Ternary phases of plutonium have been prepared with uranium, thorium, and there's also mixed carbides with nitrides, oxides, and halides. As we've already alluded to, plutonium nitride can be made from the carbothermic reduction process. The mononitride is the only known plutonium nitride with any certainty. In addition to the carbothermic reduction process, one can also produce the material in liquid ammonia from the triiodide. With this reaction, you get a intermediate amide formation, and in this, the plutonium nitride will precipitate out of the ammonia solution. This is an interesting synthesis where if you wanted to tune plutonium nitride properties, you could tune them as much as similar to a sol gel process for making nuclear fuel with certain particle size. The structure is face-centered cubic. The lattices have been evaluated, and the plutonium-nitrogen, plutonium-plutonium bond distances evaluated. The nitride has very high melting point, which is suitable for fuel. It's also compatible with steels and sodium. Again, this makes it a good candidate for fast reactor fuels. As most nitrides, it reacts with oxygen and dissolves readily in mineral acids. The 5F electrons seem to be delocalized, which is a good property for fuel. This delocalization helps with having the nitride, plutonium nitride, having good thermal properties that are compatible with what's needed for nuclear fuel. Another very important plutonium species is the oxide. The oxide can be used for storage, can be used for fuel, and as we already discussed with plutonium-238 oxide, dioxide as a power source. The oxide species are listed here. The monoxide is a minor species. We won't go into any detail. We've already discussed Pu2O3, and we can see that we've already discussed how this can form on the dioxide, where it acts as an intermediate phase. The metal and dioxide are FCC, so the FCC structure of the Pu2O3 is favored. There's another structure, a hexagonal form, that can be produced even if you have this material in the presence of the dioxide and the metal, but you would need to heat it up to 450 degrees to produce this hexagonal form. There's a way of producing the Pu2O3 by treating the plutonium dioxide with carbon, producing carbon monoxide and reducing the plutonium from the 4 to the 3. The dioxide has a wide composition range where you can have it's face-centered cubic. You can produce this from oxidation of plutonium metal. For instance, if plutonium metal is ignited in air, you will get PuO2, or calcination of a number of plutonium compounds. For instance, oxalic acid, if you calcinate precipitates of plutonium oxalate, you'll get the dioxide. However, if you precipitate phosphates, which readily form, you will not get the dioxide. So the heating rate, if you do calcination of material to produce the plutonium dioxide, will affect the composition due to the rate of decomposition and gas evolution in the material. Plutonium dioxide is olive green, and this color can vary due to particle size and impurities. And here's an example of a plutonium precipitate that already has this olive green color. And the material, plutonium dioxides, have been produced through a sol-gel method, where the nitrate in acid is injected into an organic, and microspheres are produced. One of the outcomes of this, by tuning the sphere size, is that the color of the material can be influenced. And here's our phase diagram for the plutonium. We see that it has a number of different phases, somewhat similar to the dioxide, excuse me, uranium, but some of these haven't been as studied or as identified as the uranium system. Other oxides that we've already discussed about are hyperstoichiometric and substoichiometric materials. So this hyperstoichiometric sesquioxide, so PuO 1.6 plus X, can be formed. So these are related to transition between the plutonium-3 and plutonium-4, and substoichiometric, where we have PuO2 minus X, where we can have Pu go from 1.16 to a little under 2. Again, like uranium, you can tune what that X is. The exact composition depends upon the oxygen partial pressure, and that's shown here, where over here we can see what X is. So PuO2 minus X, and X can go from 0.001 to 1, so we have a fairly large range of control. And the partial pressure shown here, the oxygen partial pressure going from 10 to the negative 8 to all the way to 10 to the minus 22. And you can use this as a guide, depending upon what temperature you'd want to produce the oxides at, as a way of tuning the exact composition of your plutonium material. Very similar to what we observed already with the uranium system. Other plutonium oxides include the hyperstoichiometric, PuO2 plus X, and other oxidized, so PuO3, PuO4. Tetravalent plutonium oxides tend to be favored. Often you're unable to oxidize the dioxide even at high pressure oxygen at 400 degrees or in ozone. However, PuO2 plus X has been reported in the solid phase. This has been related to some water reactions as shown here, and also shown here some XAFS data where we see as we go from PuO 2.00 to PuO 2.26, what's observed is the growth of this plutonium oxygen double bond here at this peak. This is indicative of the formation of oxidized plutonium species. Now, other plutonium species, the PuO3 and PuO4, have been reported in the gas phase, and primarily from surface reactions with O2, with the material going to the gas phase, and the PuO4 yield decreases with decreasing dioxygen partial pressure. The information about plutonium oxides overall are listed here with the compound, their phases, space group information, and densities. There's also a table here showing the characteristics of plutonium dioxide plus X from decomposition of different materials, so the formation from compounds, metals, sulfates, chlorides, etc., and the color and the appearance of the PuO2 plus X from these compounds. Mixed plutonium oxides can also be formed. One form that's important as a waste form is the perovskite type structure, where you have AbO3. Plutonium of different oxidation states can be incorporated into this material along with other elements, including fission products. Double perovskites have also been evaluated. And again, plutonium can sit in the B location, where other metal ions, including fission products, can be in the A location. So this makes an interesting waste form. The plutonium lanthanide oxides have also been evaluated, where solid solutions can be formed, and the levels of the solid solutions aren't over the entire range. However, for some of the lanthanides, such as cerium dioxide, you can get solid solutions over the entire range. And solid solution of plutonium has been discussed already with the uranium system, and it also behaves the same with the thorium system. An overview of the chemical properties of plutonium oxides are listed here. The thermodynamic data for the plutonium oxide system is available in the chemical thermodynamics of plutonium. And for the nuclear fuel cycle, an important consideration is dissolution. Any high-fire plutonium dioxide is difficult to dissolve. This has an implication on MOX fuel, where MOX fuel, after it's been burned a number of times and recycled, you have difficulty dissolving it. So the dissolution of the plutonium dioxides is dependent upon the temperature and the sample history. And as we already stated, this irradiated dioxide is a higher dissolution rate with higher burnup. The dissolution can often be performed with the addition of HF and other stronger oxidizing agents, electrochemical oxidation, or with the use of cerium. Plutonium fluorides are also important compounds for the nuclear fuel cycle, particularly in the preparation of plutonium metal. Here's a reaction for making the trifluoride with the dioxide, hydrogen, and HF. And if you use the oxalate precipitate with HF, you can also get to the trifluoride. At lower temperature, you can form the hydroxide fluoride of different stoichiometries can be formed. If you have stronger oxidizing conditions than what's listed here, what's listed up here, you can get to the hexafluoride. So, for instance, the dioxide with fluorine gas, or the tetrafluoride with fluorine gas at 300 degrees. Some of the properties of the fluoride compounds: the trifluoride is insoluble in water. This can be prepared by the addition of HF to plutonium-3 solution. So if you had a plutonium-4 solution in HF and you hit it with hydroxylamine, you can reduce the plutonium down to the 3 and have that, one of the results of that would be a precipitation of the fluoride compound. Purple crystals are yielded that are slightly hydrated. Plutonium tetrafluoride can be formed from the precipitation of plutonium-4 compounds in HF solutions. The compound is pale pink, that's hydrated. If this compound, if the tetrafluoride is heated under vacuum, you can produce the trifluoride, the net result being shown here. High vacuum and high temperature favors the formation of the trifluoride, and you can make these compounds, both the tri and tetrafluoride anhydrous, so you can knock off that water by treating this product in a stream of HF gas. The hexafluoride, which is volatile, can be prepared from the reaction of the tetrafluoride with the difluoride. The reaction rate is pretty fast. The fluorination rate shown here against the partial pressure of fluorine. We see once we get above 300 degrees, from 200 to 300 degrees, we increase about an order of magnitude, where the reaction rate, the reaction rate equation is shown here, and the dependence upon temperature is evident. And this material can be handled in glass. So the degree of fluorination from the plutonium hexafluoride is relatively low. The structures of the fluorides: the tetrafluoride is isostructural with the actinide and lanthanide tetrafluorides, shown here. And like uranium hexafluoride, plutonium hexafluoride has OH symmetry in the gas phase. The fluorides have melting points which are higher than the metals, right? Melting points of about 1400 C for the trifluoride, about 1000 C for the tetrafluoride, and very low melting point, high vapor pressure for the hexafluoride. The hexafluoride has been examined by IR, and isotopic shifts have been reported for the IR spectra of plutonium hexafluoride with plutonium-239 and plutonium-242. Plutonium hexafluoride can undergo decomposition from alpha decay and temperature. The exact mechanism is unknown, but this does indicate that the stability of plutonium hexafluoride is dependent upon storage and the isotope in which the hexafluoride is produced. So generally, if you were to store plutonium hexafluoride, it would be stored under reduced gas pressure. Higher halide preparation has been performed, so going from above the fluorides to the chlorides. You can get the trichloride from this reaction with plutonium oxalate. So this plutonium-3 oxalate with HCl yields the plutonium trichloride. The reaction of the oxide with phosgene has also been reported, or there's just a simple evaporation of plutonium-3 in an HCl solution. The tetrachloride, if you have the plutonium trichloride from this reaction and treat that with chlorine gas, you can get to the tetrachloride. Mixed plutonium halide salts have been examined. Here's an example of the phase diagram for the potassium chloride, plutonium chloride system. One of the interesting properties is that we have a eutectic formation. Here is the melting point of the potassium chloride. Here's the melting point of the plutonium chloride. And we see a mixture that's about almost 50% or 55% plutonium trichloride has a melting point a little bit below 500 degrees. So this is an interesting property of the chloride system and can be used, for instance, if you're evaluating a molten salt reactor containing plutonium. The chloride with plutonium can form these eutectics, which will have suitable properties in a reactor. These materials can be prepared by metal halides and plutonium halide. You can just dry them directly in a solution, or the halides and the tetrafluoride or the dioxide can be heated in an HF stream. These are for the fluoride systems. And the chlorides can be prepared with similar routes using either the tri or the tetraplutonium chloride. We'll end the lecture on plutonium chemistry with discussions on its non-aqueous system. There's relatively very little plutonium non-aqueous in organometallic chemistry. Halides, as we discussed earlier, are useful starting compounds. For instance, plutonium triiodide tetrahydrofuran, shown here, is a useful starting compound. This can be reacted with a number of compounds to form novel organometallic species, and these species can be examined to understand the electronic structure of the plutonium compounds. One of the main reasons, or one of an interesting area of research for looking at non-aqueous plutonium chemistry, is to explore the spectroscopy of the resulting compounds. Borohydrides have been prepared with the plutonium tetrafluoride as a starting compound and aluminum borohydride as a reactant. These compounds are yielded, shown here, the plutonium borohydride, and you can separate this by condensation of the plutonium complex, and IR spectroscopy has been examined, and the space group TD has been, it gives a pseudo-TD coordination space group. Other organic compounds, such as these sandwich compounds, have been produced again using the halides as starting materials. This reaction is shown here. The resulting compound has D8H symmetry, since this is a 8-membered ring, and the orbitals are dominated by 5F and 5F6D mixing, and the molar absorptivities with the FD mixing has a very high, approaching 1,000. So this would give very colorful complexes. Cyclopentadiene is also a common compound used in organometallic chemistry, and again using plutonium trichloride with molten CP beryllium, you can get the tris CP chloride as a compound. This has been characterized by IR and UV visible spectroscopy, and this compound is a suitable starting material for further synthesis. The electronic structure of plutonium compounds have been examined. Shown here is the data for plutonium hexafluoride. The orbitals, one initially would expect ionic bonding. We know from the behavior that this is not appropriate. We know from uranium system, when we've already discussed about plutonium, that it has OH symmetry, and sigma and pi bonds are formed, and the orbitals from the plutonium that form the sigma and pi bonds are listed here. And there's a range of mixing, including the contribution of plutonium F and P, along with the P orbitals from the fluorine. The spin-orbit coupling splits the 5F state, and this is a necessary component to understand the molecular orbital and the resulting electronic orbital filling. And like the uranium system, PuO2, the PuO2 cation, the eel structure is also linear. The symmetry is the same as what you would expect for the uranyl system. And the oxygen, plutonium, interacts with the oxygen, forming sigma and pi bonds, just as we saw in uranium. There's weak ionic bonding in the equatorial plane resulting from this compound, and again the orbital overlaps are shown here, and the full molecular orbital for the plutonium, the oxygen, forming the molecular orbital of the system, similar to the uranium, except we have a few more electrons on here. And then here's the extension of this molecular orbital of the plutonyl system binding with ligands. So this can be used to explore the UV vis spectroscopy of the plutonyl system. Right, taken together, all three lectures, we evaluated nuclear and isotopic properties of plutonium, the production from plutonium-238, some discussion of the fissile and fertile isotope. We reviewed plutonium in nature and how it's produced. We went over separation and purification routes. Generally, these general separations and purification routes for plutonium. Details on plutonium in the fuel cycle chemistry will be given in later lectures. We also discussed the metallic state, both the pure metal and alloys, how it reacts and oxidizes, and the role of F electrons in these states. And we just got done reviewing compounds and for the nuclear fuel cycle and solution chemistry, and how that solution chemistry can be extended to the coordination chemistry of plutonium. Some example of questions you should be able to answer based upon the 3 lectures on the plutonium series are found here. This one actually harkens back to some earlier lectures. Which isotopes of plutonium are fissile? Why? Well, the odd A plutonium isotopes are fissile because they have the unpaired neutron. Primary example being plutonium-239. How can one produce plutonium-238 and plutonium-239? So let's take these in series. So plutonium-238, one can do neutron capture on neptunium-237. That produces neptunium-238, that undergoes a beta decay, and that produces plutonium-238. Again, this is the route by which plutonium was discovered. For plutonium-239, both the production and how is plutonium produced naturally are basically from the same route. You could have neutron capture on uranium-238, and then the beta decay of uranium-239 produces neptunium-239, and then that goes on to produce plutonium-239. In a reactor, we can use a relatively large neutron flux to produce a significant quantity of plutonium-239, whereas in the environment, your neutrons can come from the spontaneous fission of uranium-238. The uranium-238, if it's in an ore with a relatively high concentration of uranium, perhaps that neutron from the spontaneous fission finds another uranium-238 which captures it, and that produces uranium-239, which undergoes beta decay to neptunium-239 and then to plutonium-239. That's why naturally produced plutonium is in extremely small quantities. And then how does redox chemistry influence plutonium? Well, you have oxidation states in solution from 3 to 7. 7 is a little bit tough to make, but it can be observed. And there's small energy gaps between the different oxidation states. So that means that they can exist at the same time. So all states can be prepared, and in many solutions they can be together at the same time. General trends are the lower oxidation states are more stable in acidic solutions. The pentavalent state is more stable in neutral solutions, and the higher oxidation states are favored in basic solutions. Also, for the pentavalent state, it's favored in dilute solutions because it can undergo disproportionation. Again, plutonium-7 is stable only in highly basic solutions with strong oxidizing conditions. Other questions that you should be able to answer based upon the lectures. Continuing with the oxidation state, how can you identify different oxidation states of plutonium? Well, as we discussed, plutonium solutions are colored. Here are the different oxidation states, 3, 4, 5, 6, 7. We see the different colors. And even for the same oxidation state, here's all tetravalent oxidation states with different ligands, so different acids, HCl, perchloric, nitric, and then plutonium colloid. We see that they're colored, they're visible, so we should be able to use UV visible spectroscopy as a means of determining the oxidation state. And here's the data for the different oxidation states and the peaks with their molar absorptivities. So we see 3 has a peak around 600, plutonium-4 closer to 650, and also at 470. Plutonium-5 around 570. Plutonium-6 is a very large peak at 830. Again, with plutonium-4, we see that there's differences in the solution colors. They're depending upon the ligand. We also know that with the colloid, you'll get larger absorbance at the lower wavelengths. So how many phases can plutonium metal form at standard pressure? Unlike some simple metals such as aluminum, where we see, for a large range there's just one phase, plutonium at standard pressure has 6 phases. and they have abrupt changes in length here as a function of temperature, which means that these are the transition points. And we also see changes in density. The densities are shown here, where the most dense phase is the simple monoclinic, and you get the face-centered cubic as the least dense phase, which is interesting because there's liquid phases which are more dense than some of the solid phases. And you can also get a seventh phase of plutonium at higher pressure. So, how do relativistic electrons affect plutonium chemistry? Well, we see that the 5f electrons are actually extended farther from the nucleus compared to the 4f electrons, and these 5f electrons can then participate in chemical bonding. As an example, here's the relativistic and non-relativistic computations for the different electron orbitals for trivalent plutonium. And the key here is the relativistic calculation is the solid line, and we see for the 5f electrons, this solid line has a probability of being shows that there's a probability of the electron being found farther out from the nucleus. And this slight change is enough for the chemistry of plutonium to include these 5f electrons. How does plutonium metal oxidize? And we've discussed the importance of understanding this oxidation. Well, the metal forms some sort of oxide layer on the metal surface, and then this oxide layer is less dense, so you can have a swelling of material. Sometimes this oxide layer can spall off, exposing more metal that can then undergo further oxidation. These oxides can be other than the dioxide, so the trivalent oxide can also form. There's also some trends. For instance, there's slower oxidation in dry air, or if you form the hydride, which can be formed obviously with hydrogen presence, or also the presence of water with radiolysis forming hydrogen, you can get a much greater oxidation rate in the presence of the plutonium hydride species. And then finally, what is a useful starting compound for plutonium non-aqueous chemistry? Well, the tetrahydrofuran compound of the plutonium triiodide. So this is a lower oxidation state plutonium species, and you can generally make this readily from plutonium metal, which means for a laboratory to perform these sorts of studies, it'd also be good to have a route for generating plutonium metal.
A question you should be able to answer after viewing the plutonium lectures is, why does plutonium metal have multiple phases? This is an important property of plutonium metal. It certainly impacts how it's used, how it behaves in conditions where it's metallic. This could be fuel, this could be within other materials of interest. And the properties of the multiple metal phases really is reflected because of the very specific chemical nature of the actinides having to do with the 5f electrons.